In this lesson, we compare two last-level cache options at equal silicon area. We have option 1, a 3D stacked 4 MB L3 with a 2 nanosecond hit time, but twice the energy per access. And option 2, a 12 MB off-die L3 with a 12 nanosecond hit time and baseline energy per access. We will decide if the 3D stacked cache beats the off-die cache using a MIS model, m of s equals a divided by s to the power 0.3, both mathematically and graphically. First, let's set up the two options clearly. We are given a scaling law for the L3 miss rate, m of s equals a divided by s to the power 0.3. This means that larger capacity reduces the miss rate with a gentle power law. Here is the model on screen. To compare apples to apples, we will calibrate the constant A. Suppose a typical miss rate at 12 megabytes is 10%. Then A equals 0.1 multiplied by 12 to the power 0.3. We can compute the two miss rates now. For 4 megabytes, M is approximately 0.139. For 12 megabytes, M is approximately 0.100. Notice the smaller cache has about 39% more misses. Performance comparison uses the average memory access time, or AMAT. For an L3 as the last on-chip cache, a simple model is AMAT equals L3 hit time plus miss rate times memory penalty. We write these two AMATs. To ask when the 3D L3 is faster, we set its AMAT less than the off-die one and solve. This gives a threshold on a times memory penalty. Numerically, that threshold is about 54. So if a times memory penalty is below 54, the 3D cache wins on latency. Let us pick a typical external memory penalty of 80 nanoseconds to get concrete numbers. Using our calibrated miss rates, we find AMAT for 3D is about 13.1 nanoseconds, and for off-die it is about 20.0 nanoseconds. So on latency, the 3D option is clearly faster for this regime. Now, let us visualize the entire AMAT as a function of memory penalty. Next, energy per memory reference. A simple model is that each access pays for one L3 lookup, plus, on a miss, you pay a main memory energy. The 3D cache uses 2 times the L3 energy per access. The off-die cache is our baseline. So we model energy per access as E sub 3D equals 2 times E sub L plus M of 4 times E sub MEM. E sub off equals E sub L plus M of 12 times E sub MEM. Because M of 4 is larger than M of 12, the 3D option always uses more energy per reference in this simple model. For a concrete example, if a main memory access costs 50 times an L3 access in energy, then the energy ratio 3D over off is about 1.492. So energy only favors the larger off-die, L3. A useful combined metric is the energy delay product. We multiply energy per access by the AMAT. The ratio of 3D over off is the energy ratio times the AMAT ratio. With the same example numbers, the AMAT ratio is about 0.656, and the EDP ratio becomes about 0.979. Values below 1 favor the 3D option. Let us graph how these ratios change as we sweep the main memory energy, factor K. Let us summarize. On performance, the 3D stacked 4 MB L3 is faster than the 12 MB off-die L3 across a wide and realistic range of memory penalties. The crossover condition is a times memory penalty less than about 54, which is easily satisfied for typical programs and memory systems using our calibration. On energy per access, the 3D option does not win in this simple model. It spends twice the L3 energy and also suffers a slightly higher miss rate. For energy delay product, the winner depends on how expensive main memory energy is relative to an L3 access. When main memory energy is high, the strong latency win from the 3D option can overcome its higher energy per access. When main memory energy is low, the off-die cache can be better overall. In short, 3D stacked 4 MB L3 beats the 12 MB off-die L3 on latency. Energy is worse, and the combined energy delay product can favor 3D if memory energy dominates.